All right, so let's start. Welcome back. I hope you had a nice, relaxing holiday. I hope you got to spend some time to relax, to take your mind off mathematics, and to enjoy some things that you probably like better than math. Just a few organizational remarks. As usual, before we start, I'll point out that exam registration is still possible one last time. Deadline is 15th of January, and please remember, if you have not registered for the exam, you will not be able to take the exam. And as I'm getting asked that frequently, if you choose to just do the second attempt, that is totally fine. You don't have to register or be present for the first attempt. You can just choose to register for the second attempt only if you want to do that. However, I'd like to point out that your next chance to take this exam will be a year from now. So there is no attempt for the Math 1 module in the summer term. We only have these two, and then the next chance will be in the year after this. Also about the exam, in case you have been granted a disability accommodation by your examination committee, then please let me know about that. You should have gotten a letter stating your specific disability accommodation. Please just send that to me, preferably by email. In case you don't know, this is my email, michael.ritter@tuam.de. Just send me that letter so that I can make sure that you receive the disability accommodation that you're entitled to. All right, so let's start with today's topics. Remember, before the Christmas holidays, we did start to talk about calculus. Specifically, we started discussing sequences and then series and limits of sequences and series. This week, we're pretty much going to apply that to talk about limits of functions. That is probably a topic that you've heard about in school already. So I'm guessing that that should be more or less familiar to some of you at least. And next week, we'll then talk about, hopefully your favorite subject, differentiability, and what can be done with differentiable functions. So limits of functions, basically that's just an extension of limits of sequences. As a quick example, I sketched down a function. Basically the most important part is how it is defined. And that is an example of how a piecewise function can be defined. So if you define a function through a term, you don't have to do it through just one single term. You can have multiple cases, and of course you need to make sure that those don't overlap anywhere. So in this case, we have two parts to this function definition. The function is defined on this interval from 500 to 2000, boundaries included. And from 500 to 1000, the function term is 3x. And for 1000 to 2000, you get a different definition. This one here, 2500 plus 2 times x minus 2 times 1000. Please pay attention to the fact that the 1000, this right boundary, is included here in that first case and not included in that second case. So those don't overlap. This notation here means the boundary is not included. This notation means the boundary is included. If you make a sketch of this, you'll see that looks basically like this here. For the graph of a function, I usually denote values that are included or not included by drawing them like this. So this point here is filled in. And the idea is to denote that this is the actual function value here. This is not filled in, so that means there is no function value at this point, rather that is here for this x value. And of course, the values at the boundaries, those two are included, so I've filled in that. Yeah, so that's what I'm usually going to use, and of course you can do that as well if I sketch a function. And you'll see this function is one that has a jump here in the middle. So first the slope is like this, and then it jumps down a little, and the slope also changes slightly. And basically the question is, how do we deal with functions like that? And similar to what we did with sequences and series, we'll define what we mean by the limit of a function as x tends to some specific value. And specifically say a function is convergent for x to some x star, and that can be any value in the domain or not in the domain. If there exists some value, I call that gamma here, the intention is that this is the function value in the limit, and that has the following property. This gamma is the limit of a sequence of function values, f of xn, and the xn are an arbitrary sequence somewhere in the domain of that function without x star, the point in question. So we choose a sequence that converges to x star. You just evaluate f at that sequence, you get another sequence of function values, and then you compute the limit of that. And if that limit exists for all possible choices of sequences, so this every here, that is important, then you call this value the limit of the function as x tends to x star. All right, sounds complicated, but it's actually not. Similar to sequences, you mostly need a set of tools, and most of those will be similar to what we did with sequences already, to compute these function values and see if they exist. All right, also similar to sequences, the notation just looks like that. Limit f of x, x tends to x star equals gamma, or you can also write f of x tends to gamma as x tends to x star with this arrow notation here. And also similar to sequences, we also have one-sided limits. And basically that means we restrict ourselves to sequences that are either below x star or above x star. And we call this limit from below or from the left, and the limit from above or from the right. Yeah, basically that's it. The notation for that, for the limit from below, I usually use this notation here with an upwards pointing arrow. You can also use this notation with a minus up here. They mean the same thing. And for the limit from above, I use this notation with an arrow pointing down. Or you can also use this notation with a plus. Okay, so those are one-sided limits. And the one important thing to remember here is that a function has a limit if and only if the two one-sided limits exist and have the same value. So if you look at this function here as an example, of course the interesting point in this case is this x value, right? So this is our x star. That is exactly the value 1000. Right? This is where the definition changes, so that's where interesting things might happen. And if you look at the limit from the left or from below, you get this point here. Right? You approach, basically the function values approach this point. So locally, it looks coming from the left, it looks like the function should have this value, so that is the limit. And incidentally, that is the function value at this point. If you come from the right, again, the idea is to look locally what the function value should be if you approach from the right, and you'll find this value here would then be the limit coming from the right. So in this case here, those two limits, left and right limit, those don't agree. So the one-sided limits are different. And that means if you compute the limit of f of x as x tends to 1000, this does not exist. Right? So the function simply does not have a limit in that case. It does have two one-sided limits, it does not have one limit. If the one-sided limits would be the same, then the limit would exist. And it would be that same value, of course. All right, so function limits, and of course you can also use basically the same notation as with sequences. If a function is unbounded in either positive or negative direction, so if the values get higher and higher, we say the function tends to plus infinity. If the values get lower and lower, we say the function tends to minus infinity. As with sequences, we would denote this by this limit notation here, but the limit does not actually exist. So if I'm asking, does the limit exist, and it turns out to be infinity, then you would answer, well, the limit does not exist. All right, and of course, you can also ask for the limit as x tends to plus or minus infinity. In that case, for the definition, you just use sequences that are unbounded, that tend to infinity or minus infinity. And you might also get a finite value, and then that would be the limit of the function as x tends to plus or minus infinity. All right. Couple of rules for function limits. Again, basically, that is how you would intuitively use function limits. So that shouldn't be surprising. And they're the same as with sequences. So what it says here is if we have two functions, f and g, and we consider the limit as x goes to x star for both of these functions, and if both of these functions have limits at x star, then we can just use the usual operations on those limits, right? So the limit of the function that we get as by adding f and g or by subtracting g from f is the same as the sum or the difference of the individual limits. Same is true for multiplication. Same is also true for dividing f by g if that limit does not happen to be 0. Of course, you can't divide by 0. It's also true for the limit. But if that does not happen, you can just split that up. And of course, all of these statements also apply to one-sided limits in the same case. Right? And again, similar as with sequences, there's also a sandwich theorem. And that basically says, well, if we have two functions, three functions actually, such that the limits for two of those exist, and one happens to be below the other at all times, then of course that same is true for the limits. And if that third function happens to be sandwiched in between those two, then it doesn't have a choice. It will also have a limit, and this limit will have the same value as those two if they converge to the same value. Right? Think of something like, let's make a quick sketch here. Say we have a function, for example, that looks like this. So this is my upper boundary. This is my lower boundary. It's just a constant function. That's also fine, of course. And let's say we have a function that behaves something like this here. So it oscillates between those two. Oops. And we're interested in the limit at this point, x equals 0. Right? And you can see that function is bounded below by this one, bounded above by this one. Both of these functions happen to have a limit at 0, which is equal to their function value. And that limit is the same, 0. So that green function doesn't have a choice. It will also have a limit at 0, and it will be 0. Right? So same as for sequences, the sandwiching also works for functions. We'll probably need that pretty rarely, just for the sake of completeness. And there is an example on the exercise sheet about that one. All right. So that's basically the definition of limits. A couple of examples. We've already looked at this example here. This was the function with this jump here in the middle. I've already said that the limit coming from below at 1,000 is this. Coming from above, we have this value here. And And that means the function does not have a limit at this point, it just has one-sided limits. It does have a limit at all other points in the domain, of course. And that's simply the function value. Right, so here's the computation. Basically, you just substitute the value for x into the function definition and you get the right value. All right, here's an example of how to apply those rules of limit computations. In this case, you have a function that is composed of several other functions. So you have a division of this function and that function, and you know if both of these limits exist. Well, the function does have a limit, and it's simply the limit that you get by dividing the individual limits. And then you can split that up some more. Each of those functions is a sum. So the limit of that function exists if the limits of the individual summands exist, and you can just get the limit by splitting it up. So what we do is we apply the value limit to this function here, to this function here, to this function here. This is just a constant, so of course the limit will be that constant value. Here, in that case, we took out the 2. Again, what we did is apply the multiplication rule, right? The limit of 2 is just 2 times the limit of the inner function, and then we took apart that inner function once again, x times x. So the limit of that exists if those individual limits exist, and then the value is just the product of those two. Right? So that is what we do, and of course we won't write that down anymore in the future, just to clarify that here we are using those rules. Basically, in this case, all we have to do is we substitute the value for x here, so we just substitute 1 in these places. We get a finite value in both numerator and denominator, 6/3 in that case, and that's 2. So we can just determine the value through a simple computation. Of course, things would get more interesting if we don't get finite values, or if we get 0 in the denominator. That's when interesting things start to happen, and we'll have examples of that. So here's one. Again, we have a rational function here. We want the limit as x tends to 1, and the difficulty here is that x minus 1 tends to 0 as x tends to 1, so we can't apply that rule anymore, right? The limit would be 0, and we can't divide by 0. So one very common technique in this case is to see if we can figure out whether the numerator here can be decomposed in a way that takes out this factor here, x minus 1, so that we can then reduce by x minus 1 and get rid of the denominator that is troublesome. Right, that's the idea. And that is true if this x value happens to be a root of this. And of course, that is the case here. So we consider that x to the power of k minus 1, and then set x to the value of 1, then we get 1 to the power of k minus 1. Of course, that is 0. Right? So there must be some decomposition of x to the power of k minus 1 in the form x minus 1 times some other polynomial term. So we can basically just take out this factor here. That's called a linear factor. Somewhat misleading. An affine factor would probably be the better name, but that's just how it is. So we take out this linear factor here, and then we reduce. And well, in this case, this is what you get if you take that out. Should be easy to convince yourselves that this is true if you just do the multiplication here. I'll show you with an example later on of how you could obtain that. Right, and then you just have a polynomial, and of course in that polynomial, you can simply substitute that value once again. A polynomial has k factors, so you get 1 for each factor if you do the substitution, and that means the final value is k in this case. Okay, so reducing a fraction is one of the tricks that we'll use pretty often. Another trick that you are familiar with from sequences is this one here in D. What we have here is an expression that involves a square root. And again, the complication here is that as x tends to 0, the denominator tends to 0. And also, this value here tends to 0, right? So this is the square root of 1 minus 1, that's also 0. That means it's not easy to predict what will happen here, and we'll have to simplify this expression somewhat before we can say something about it. And the usual trick to get rid of these square roots is to apply a binomial formula. You will hopefully remember that binomial formula here. A minus b times a plus b is a squared minus b squared. That's the formula we use here. And through these squares here, we'll get rid of the square roots. So we take this expression, that's our a minus b, and we just multiply this by a corresponding a plus b. And of course, we'll have to divide by a plus b so that this doesn't change the expression. So basically what we do is we multiply by 1 and we write that 1 in a very sophisticated way to achieve what we want to achieve. And what happens is, well, you apply this formula here, you get rid of the square root at least in the numerator. You do obtain a new square root expression here in the denominator, but that doesn't hurt you because it does not tend to 0, right? That's a nicer square root expression. All right, and what happens is we get x plus 1 minus 1. So this is the simplified expression, and now you see we can get rid of that x value. You just cancel that out. So all we have is 1, and that's a constant. That's much nicer. And here we have an expression that does have a limit that is not 0. So we get 1, and the limit here is 2. By just substituting x, we get 2. And that's it. So the limit here is 1 over 2. Again, same trick that you should already know from sequences. That's something that you also frequently apply with function limits. All right, any questions so far about function limits? Otherwise, maybe let's have a quick look at the homework problems. So in 11.1, I'm asking you to compute the limit of 2 functions. And as usual, I'd like to know whether you got the right result here. So let's start a quick tweet back. Let me just switch to that. So for the first question, 11a, what is the limit that you got? Tweetback should now be online. Give you maybe a minute to answer that. All right, let's take a quick look at your answers here. This is what you have. So most of you say the limit is minus 4 over 3, more than 50%, and those are the people who are correct. So this is actually a correct result. A couple of people said 0, surprisingly. Maybe it would be worth having a quick look at that problem. So part A, here we have, let's see, the limit of x to the third minus 7x plus 6 divided by x squared plus x minus 2. And we want the limit for x tending to 1. So the first thing that you do is you just plug in x and see if that gives you a result already. Right, so if you do that, you get this here, this factor will be 1. Here you get minus 7, and here of course you just get the constant 6. Here you get 1, here you get 1, here you get minus 2. So what happens is the numerator goes to 0 and the denominator goes to 0. Right, so with the denominator going to 0, unfortunately that means we can't apply that rule that we can just determine the limit by dividing the individual limits. Not possible. So we have to figure something else out. Well, we do know, however, that 1 is a root of both the numerator and the denominator. So we can try to factor that linear factor out and then cancel it out, hopefully. Okay, so what we found is 1 is a root of both numerator and denominator. So what we want to do is we want to factor out that x minus 1. We do that for both polynomials. Let's start maybe with the numerator. So we have x to the third minus 7x plus 6. And we want to write that in the form x minus 1 times something that we still have to figure out. Right? So what we need to do is what is known as long division or polynomial division. So we divide that expression by x minus 1 in a way. And we do that in the following way. First we take a look at this leading coefficient here, that's just x to the power of 1, and this leading coefficient, x to the power of 3. And we figure out what do we need to multiply this with to get this. So in this case, x needs to be multiplied by x squared to get x to the third, right? So this is the first factor that we have, x squared. Yeah, simply because x times x squared is x to the third. And maybe I can write this in a more legible way. Yeah. All right, so now let's see what this factor x squared already covers. Well, if we multiply x squared and this expression here, x minus 1, what we get is x to the third minus x squared, right? So this is kind of the part that is covered by x squared, so we subtract this part from our polynomial. And what remains is minus x squared minus 7x plus 6. And of course that's a plus x squared, I'm sorry, yeah. All right, and then we just continue in the same way. Again, we look at the leading factor here, that is x squared. And here we have an x, so what do we need to multiply this x with to get x squared? Well, the next factor should obviously be an x plus x. So that's what we write here, plus x. Yeah, simply because x times x is x squared, right? And this here, this is the factor that we have here. And this is the factor that we had here. And again, we figure out what we covered with this. So what we do is we multiply x with x minus 1. And we get x squared, as expected, minus x. So we subtract that from our remainder. And we get, let's see, minus 7x plus x, that's minus 6x plus 6. So we're still not done. Next, we need to reproduce this minus 6x here. And again, the question is, what do we need to multiply x with to get minus 6x? Well, of course, the answer is minus 6. Right? And that is because, again, x times minus 6 is minus 6x. This is this minus 6x here. All right. And again, we multiply this minus 6 by x minus 1. We get minus 6x, and we get plus 6. And then we subtract that from our remainder. And this time we get 0. Right? And that means we have covered everything. Right? So multiplying this and this expression will yield this polynomial here. And that means this is the expression we've been looking for. And of course, if you don't get 0 by the end, you've probably made a mistake somewhere. Either that linear factor is not actually a linear factor with a root, so might mean that accidentally you thought one was a root, but it isn't, or you made probably some mistake in here. So if that works out at the end, at some point you should get 0. All right, so this is what is known as long division, and that is how you can work out these linear factors. Okay, let's do the same thing just for practice with this other polynomial here, x squared plus x minus 2, this one here. X squared plus x minus 2. And again, we want to divide that one by that factor x minus 1. And again, what we do is we look at this first expression here, x squared, and this x here. And the question is, what times x is x squared? Well, the answer is x, of course. X times x is x squared. Then we subtract x times this expression from our existing polynomial. So x times this expression is x squared minus x, and this is what we subtract. So we get 2x minus 2. And now to get this 2x, we need to multiply x by 2, right? So we get a plus 2 here. 2 times x minus 1 is 2x minus 2. And again, we subtract that from our remainder, and we get 0. So we're done here. And that means x squared plus x minus 2 can be written as x minus 1 times, and here's this expression that we computed through our long division, x plus 2. Right? And that will enable us to cancel out that factor x minus 1. So what we get here is the limit. Let me just write that down once more. of these two expressions here is the same thing as, well, in the numerator we achieved x minus 1 times, what was that, x squared plus x minus 6. And in the denominator we got x minus 1 times x plus 2. Oh, and I forgot the limit. So we can now just cancel out that x minus 1. We get the limit of x squared plus x minus 6 and divided by x plus 2. And now, again, if we try to just substitute 1 for x, what we get here is, well, this is 1 plus 1 minus 6, that is minus 4. And here we get 1 plus 2, so that's 3. 2 finite values, and that means we just get a value of minus 4 over 3. Okay, so basically all you need to know is when you have a root, you can factor out a linear factor by using this long division scheme. And of course, for the denominator, that's a quadratic expression. You could also just use what you know as the mid-dot formula to determine the two roots, and then you'll immediately know it can be written this way. That's totally fine, of course. All right, any questions about this one? Otherwise, let's take a quick look at the next one. Let me switch that off here. So here we have a limit of x minus some square root expression, and I guess if you've paid attention, you should be able to figure out what to do here. First, you can easily see if you just plug in x goes to infinity, you get an expression like infinity minus infinity, and that means everything can happen. So you have to apply some little trick to simplify that expression, and let's see if you found the right trick. Again, there is a tweet back, and I'll give you a minute to answer that. While you answer that, let me quickly discuss one of the questions that I see a lot online. In different variations, you're asking, can we also apply L'Hopital's rule? And some of you obviously don't know L'Hopital's rule yet. So rest assured, you can, of course, also use L'Hopital's rule. We will discuss that, I think, next week or the week after that. The reason is, of course, for L'Hopital's rule, I first need to introduce derivatives and differentiation, so I can't use that right now. We have to talk about differentiation first, and then we talk about L'Hopital's rule, and of course, you're allowed to use that on the exam if it's easier. All right, so this is why this week we only use limits that can, or ways of computing limits that can be done without applying L'Hopital's rule. Okay, let's have a quick look at the results here. Most of you say the limit is 3, and as usual, most of you are correct. The limit should be 3 in this case. Maybe still a very short look to at least give you an idea of what to do in case you didn't figure that out. So I already mentioned, basically this is an infinity minus infinity expression, limit of x minus that square root here. And I might have to write it in this way to clarify what I actually mean. So as I already mentioned, what you do in situations like this is you want to get rid of that square root expression. And the way to do this is you use a binomial formula. You multiply with that same expression, but now with a plus instead of a minus in the middle. Right, so the important fact is we've changed this here to a plus. And then we divide by the very same expression. Just a second. Yeah, that's much better. So that all we actually do is multiply by 1, right? So this here is equal to 1. And then we apply this binomial formula, and that will get rid of the square root in the numerator in this case. We get x squared minus the square root squared, so the square root just vanishes. And of course the new denominator stays as it is. And then you can just go on in the usual way, and you'll find that the limit is 3. I guess I can skip those intermediate steps, unless anyone wants to see them. Does not seem to be the case. All right. Of course, they will be included in the suggested solutions. Good. I guess we can move on. Yes. So if you have limits with sine and cosine, often the way to go is L'Hopital's rule, actually. We'll have examples of that when we cover that rule. More questions? Yes. How I get rid of what exactly? Of this here or? In the denominator, this one here. Okay, maybe let's do this intermediate steps after all. Just a very quick look. Yeah, so what I do here is another standard method, basically, that we've also talked about when we talked about sequences. First, I'll simplify a little, of course. You can see this x squared here. I'll get rid of that easily. Let's maybe write that down first. And what I get then is, let's see, that is 6x plus, no, sorry, minus 25 over that denominator expression here. Just copy that one. All right. And now I still have something like infinity divided by infinity, so I still don't know what that is. What I can do then is I look at the highest power of x and I divide by that highest power. You remember we've done that with sequences as well. So in this case, the highest power is we have an x to the power of 1 here, an x to the power of 1 here. Here we have the square root of x to the power of 2, so it's also x to the power of 1. So that is the highest power, right? So we divide everything by x. Right? And what we get then is, well, in the numerator we get 6 minus 25 over x. In the denominator we get a 1 here. If we take that 1 over x into the square root, it will become 1 over x squared. Right? So this is, let me just write that down maybe, that's the same thing as the square root of 1 over x squared. And just as a quick aside, x is tending to infinity, so we can safely assume that x is positive. Right? We're only interested in high values of x anyway. That means we don't have to take care of the sign here. So we take this into the square root, and that means in the square root we divide by x squared. So we get 1 minus 6 over x plus 25 over x squared. And of course, the reason for doing that was if we have an expression like constant over x and x tends to infinity, then that expression goes to 0. We've talked about that with sequences already. So this here will go to 0. Of course, the constant 6 will go to 6. The constant 1 will go to 1. Same thing here. This will go to 0, and this will go to 0. Right, so we get something like 6 over 1 plus the square root of 1. And of course, that's just 6 over 2 or 3. Right, so that's how I get rid of that expression in the square root. All right, more questions about function limits? Otherwise, I suggest we quickly discuss continuity and then take a look at some more examples. All right. So, continuity, let me scroll back here. So continuity is actually a concept that is of major importance on the one hand, but it will rarely show up on its own in actual examples. Most functions that we'll discuss will be continuous, simply because they're also differentiable. Discontinuous functions are pretty rare, and if we have discontinuous functions, we mostly encounter some that will jump at certain points, right? So things like this piecewise defined function that we've discussed earlier, that's an example of a function that is not continuous everywhere, but almost everywhere. Basically, the idea is a function that doesn't behave in an unexpected way is continuous. And well, how would you figure out how you would expect a function to behave? Well, what you do in calculus is, if you want to figure out something about a certain point, something about a certain function value, you look at values around this one. And then you figure out from the values in the neighborhood, how would I expect the function to behave at this point? Or in other words, what you do is you look at the limit. Right? So if you want to know what the function at this point is supposed to look like, you look at the limit as you approach this point. And if the function behaves as the limit suggests, then we call it continuous. A simple way to say that could also be something like, well, if you can draw the function without lifting your pen, and I obviously can't do that here, so I have to lift my pen here to make this jump. If it doesn't have any jumps, then it's continuous. Right? It behaves how expected in a way. And it doesn't behave as expected here in that point, because coming from the left, you'd expect it to be here, and that's nice. But coming from the right, you'd expect it to be here, and that's not the case. So in that point, it doesn't behave as expected. You wouldn't even know how to form an expectation because you get a different expectation coming from any of the sides. Yeah, so that's a non-continuous function here. Formally, that's basically the definition. A function is called continuous at a certain point in its domain if the function value at that point is equal to the limit as x approaches that point. Right? So this is kind of the expectation, the expected behavior, and this is the actual behavior. If those agree, then the function is continuous at that point. Of course, you can also define left and right continuous similarly to left and right limits. So if you just consider the limit from the left and the behavior is consistent with that limit from the left, then it's left continuous. If the behavior is consistent with the limit from the right, then the function is right continuous. If it's both left and right continuous, then it is continuous. And most often, we'll have functions that are continuous at certain discrete points, but they're not continuous at certain discrete points, but almost everywhere else. So a function is called continuous on some set, on some interval usually, if it's continuous for every point of that set. So this function here, for example, that one, that is continuous in this closed interval. It's continuous in this interval, but it's not continuous at that specific point here. Right? And of course, if you're talking about boundaries of an interval, you can only form a one-sided expectation, right? So if I'm just looking at this interval here, about this point, I could only say, well, this is left continuous because as I approach it from the left, it behaves as expected. I can't say anything about right continuousness by just looking at this. If I look at this interval, then the function is not right continuous because at this point, it doesn't behave as expected. Right? So this is non-continuous here, but it's continuous everywhere else. And of course, I can repair that situation. Well, in this case, I'd have to move at least one of those so that the function values actually coincide. So this would be a similar function that is now continuous. But of course, I changed some other function values as well, not just this one. Right? I can't repair that jump by just changing the value here. Whatever value I choose, I always get into difficulty somewhere. All right? So that's continuity. And again, operations on functions basically preserve continuity. So if you have continuous functions and you add them, or you subtract them, or you multiply them, or you divide them, as long as one is not 0, then the result is always continuous. The same is true if you, of course, apply multiplication with a constant. And the same is true if you compose functions. So if you have two functions, you compose them by first executing one and then the other on the result. Then again, the result is continuous. So if you want to figure out whether a function is continuous or not, you'll usually resort to this theorem and you'll say, well, this is a composition of continuous functions, so it is continuous itself. Okay, that's most often the case. Quick notation here. The set of all continuous functions on some interval, I, is denoted by this notation here, C0 of I, or just C0 if it's clear what we mean by I. This is called the space of continuous functions, and that is a vector space, just as a side note. Because composition of continuous functions, again, yields continuous functions, so all is fine. This, just as a side note, again, this 0 here comes from the fact that we'll use the same notation for differentiable functions. The set of differentiable functions will then be denoted by C1. Set of 2 times differentiable functions will be C2, and so on. And well, continuity basically is one step below differentiability, so that's 0 instead of 1. Okay, a couple of easy examples. Of course, a constant function is continuous, right? Because the limit is always that constant, and that is always also the function value, so nothing can go wrong there. The function that just maps x to itself is also continuous, again, because the limit of x as x tends to some x star is always x star, and that is also the function value. So again, nothing surprising happens here. And from these two, you can easily say, well, all polynomials are then continuous everywhere, right? Because they are compositions of these two. And from that, you get that all rational functions are continuous almost everywhere. Only exception is the roots of the denominator. You have to exclude those. Yeah, everything else is fine. So rational functions are continuous on or without the roots of the denominator, possibly. They might still be continuous there, but we don't know. Here's an example for a non-continuous function, the floor function. The idea is simply if you have a non-integral number, you just round down to the nearest integer below that, right? So the floor function applied to 1.7 is just 1. The floor function applied to an integer like 5 is just that integer. Only case you need to pay some attention to is negative numbers. So if you have something like minus 1.7, again, you round down to the nearest integer, always round down. So in this case, you round down to minus 2, not to minus 1, it's minus 2. All right, and well, if you take a look at that, you can see that floor function is, of course, again, continuous on every interval between two integers. It does jump at every integer, right? So what you get if you draw that function, you get something like that. So here 0 is mapped to 0. Then everything less than 1 is also mapped to 0. At 1 we jump. So here's a jump to the point 1. So this is where 1 is, right? This is where 2 is, and again we jump. So this is how that floor function looks like. So you can see that is continuous if you come from the right. So that's an example of a right continuous function, but it's not left continuous in those points. It is continuous in these intervals here, of course. Just at those integers, we have the jumps, those are the discontinuities. All right, well, here's the chart. Similar for the ceiling function, basically that's the same thing, but now you round up instead of down. And of course, all that changes is if you round up, you basically get the interval to be close on that side. And of course, it looks like this now. You jump up earlier. Right? So another example for a discontinuous function. Discontinuous in all the integer points. In this case, that would be a left continuous function, but not a right continuous one. And just to show you that being continuous is not a property that every function just has. Here's an example for a function that is nowhere continuous. It's defined on the set of real numbers. And the definition is simply, well, it has the values 1 and 0. It takes the value 1 for every rational number and the value 0 for every irrational number. And those numbers lie dense, meaning basically that in the neighborhood of every rational number there are irrational numbers, and in the neighborhood of every irrational number there are rational numbers, no matter how small these neighborhoods are. So that means it jumps up and down basically around every point. Right? So this is continuous nowhere. Right? Just as a strange example. We won't actually need that. It's just an example to show you that not every function has to be continuous almost everywhere. But the functions that we will deal with are usually functions that are continuous with the exception of just a couple of points. All right. And of course, the question that we'll encounter often is the question, given a function that may not be defined everywhere, usually a rational function that has a couple of roots in the denominator, is there a way to extend that function in a continuous way? So can we kind of mend these gaps in the function? And that is called continuous extension. Simple example, take a function like that, x squared divided by x. That is defined everywhere but 0. We can't divide by 0. But of course, if x is not 0, well, we can easily reduce that by just factoring out x and then canceling it out, and we get this expression here, same thing. So we can, in other words, we can easily compute the limit. This function does have a limit for x to 0, and that limit is 0. So if we just extend it by saying, well, that function takes this value on its domain, with the exception of 0, and it takes this value, the limit, on 0. Then we have a new function formally. We mended that gap, and that function is called the continuous extension. Basically, we mend the gap in the way that is suggested by the limit. If that is possible, we call that new function the continuous extension. Of course, it might not be possible. Remember that jumping function, there is just no reasonable limit that we could use. Okay, and a pretty common question is, again, given some function, is there a continuous extension to mend some of the gaps that it has? And what would that extension look like? And again, you'll usually answer that by taking a look at the limits, computing the limits, and using those as extension if they exist. It's not really hard, hopefully. A couple of examples. So here's again a function of rational function including a square root here. And the question is, of course, you have to exclude 0 from the domain because we divide by x. So can this be continuously extended to mend that gap at 0? Well, what we have to do is we have to compute the limit as x goes to 0. We do this using this standard trick again. Seen that before? And we get this actually has a limit, and the value is 1/2. So that means f can be continuously extended into 0 by simply setting this as a function value at 0. Right? So that's all there is to it. If I'm asking, can the function be continuously extended, at that point you just try to compute the limit. If you find one, here's your extension. Yeah. This one here? On the right-hand side, I wrote, well, that's because I reduced this x here. Right? So in this, if I just substitute x here, I still have 0 divided by 0. That's not meaningful. I can't compute that, so I just reduce that, and then I have a 1. More questions? Wonderful. So here's another example just for the sake of completeness. Function 1/x. Again, obviously not defined at 0, but everywhere else. And now if you try to compute the limit of that function, in this case we look at the individual limits from above and from below. And we can find out, well, in this case, if we approach x from above, this gets larger and larger and is always positive, so this tends to plus infinity. If we approach it from below, this gets larger and larger in absolute values, but it's always negative, so this goes to minus infinity. Right? And that means there is no continuous extension to 0 because simply there is no limit. If you look at the graph of that function, basically that looks something like this. You have these two different parts. Yeah, so obviously at 0 there is no meaningful value that you could use to mend that gap. So this is a function that doesn't have a continuous extension to 0. All right, questions about continuity? Otherwise, I'd say don't worry about that too much. Basically, if I'm asking about continuity or continuous extensions, mostly the answer will be compute appropriate limits and then take your answer from that. Yeah. So if I do find a point to extend that, well, I don't know what the graph for that function looks like, but conceptually, there would be something like a function. I should do that at 0, of course. Something like a function that misses a point, yeah. So that looks like it just has a gap where that doesn't have to be a gap, yeah. And that's a function that can be continuously extended by just filling in that gap. That's what happens here. If you consider this, we had this for example, x squared over x, right? If you draw that, what you get is, well, it just looks like the function x maps to x, like this, but it has a hole here. And of course, you can just fill in that hole. Yeah, that's what it looks like in the graph. Any more questions about that? Otherwise, let's take one more look at the homework. I still have time for that. So the second question, that was about more or less about continuity. So in this case, we have a function defined piecewise on the interval from 0 to infinity, plus infinity. So between 0 and 1, we have this first part of the definition, and at 1, we have a specific value, and for values larger than 1, we have a different expression. And the question here is, well, is this function continuous at 1, basically? So to answer that, we'll have to find out whether it has a limit at 1 and whether the limit is equal to the function value that we prescribed. And of course, we can easily do that by computing the left and the right limit, because we have different definitions for the left and the right part. So it's probably the best approach to do that in 2 different computations. Compute that limit, see if it exists, and then just see if it has the same value. And if that's the case, the limit exists. And then, of course, we still need to compare that to the function value of 2 here and see if that is the same. Right? So that's conceptually how you would do that. And usual question, let's see if you did do that and what you found out. Is the function actually continuous at x or not? Yeah, I'll give you a minute to answer that and maybe take a quick look at the online questions in the meantime. All right, quick look at your answers here. Most of you said this function is not continuous at 1, and as usual, most of you are right. This function is not continuous at 1. Maybe let's still have a very quick look at that because someone asked for that. But before we do that, I'd like to quickly address 2 other questions that came up. One question asked about, where was it? Yeah, so one question asked about, I think it referred to this problem here. And I said 1 is a root of both this expression and this expression. And they asked about how we found that root. Maybe it helps if I just clarify that the English expression root is the same thing as Nullstelle in German. So that means the function, if we just substitute that value, the function takes on a value of 0. Right? That is what I mean by root. And how I found that, well, I need to compute the value as x tends to 1. So first approach is just substitute 1. And if I do that, I find that this expression assumes a value of 0. So obviously 1 is a root of that expression, right? Because the value becomes 0. Same thing here, the value becomes 0 if I just substitute 1, so I get this root here. Of course, that's basically by chance, right? I get this one for free. If the question was, given this polynomial, find a root, things might be much harder. As long as the polynomial is of degree 2 or less, you should have a formula for that. If it's degree 3 or higher, well, your best luck is taking a guess and then doing this long division thing to reduce it and hopefully get to something that's easier. In reality, of course, if you want to find roots of higher degree polynomials, what you would do is you would use some numerical approximation. One example of that is the bisection method that we'll also discuss this week, probably tomorrow. But there are other and more involved methods to do the same thing. Finding roots of polynomials and more involved functions is actually something that happens a lot in applications and that is usually done numerically. Right? So for you, in the exam, it's mostly taking a guess. Usually, if you need to guess, it will be an integer. So 0, 1, minus 1, 2, minus 2, and maybe 3, minus 3, probably not more than that. Well, that's your best guess here. Or as I said, using a formula as long as you have a degree 2 or less. All right, so that should cover this root thing. Then someone asked another question, and that was, is the function 1 over x, is that a continuous function? And the point why I picked this question to answer is the answer is not as easy as it might seem. I have sketched that function before. You might remember it looks basically like this here, right? So your first and hopefully correct answer would be, well, this is obviously not continuous because here's a jump at 0. However, the answer to this question depends on the domain of the function, obviously. So as in many, many cases, if you ask whether a function is continuous, you need to include the domain in the function definition. So if I ask, is this function with a domain of R without 0, sorry, I should of course exclude that one. It's not defined there. Is that function continuous? Well, then the answer is no, because there is a jump, obviously, right? I could also ask, is the function from 0 to infinity f of x equals 1 over x, is that continuous? And that means basically I'm concentrating on this part here. Well, then the answer is yes, of course that's continuous. So I have two continuous parts in a way, and I have this unfortunate jump in the middle. So if that point is covered in a way by my domain, then of course it's not continuous. It's not continuous at 0, and it can't be extended continuously into that point. But it is continuous everywhere else. Right? So again, I shouldn't just say a function is continuous. I always have to include the domain in my statement or in my answer to make it precise. All right, and was there one more thing? Yes, the one asked for 11.2. We can discuss that right now. We did discuss L'Hopital rules already. Oh, one more thing. There is a couple of questions coming up on the exams that I've posted before the holidays. So in case you haven't noticed yet, on the Moodle page I've posted some exams of past years. Not all of those are mine, but I'd say mine should be pretty similar to that. Mostly as exercise material. Unfortunately, I don't have solutions that I could publish for those exams. As I said, either they're just not mine, or I kind of lost the solutions, or I just have them in a form that I can't publish for a couple of reasons that I don't want to go into. However, if you'd like me to discuss one of those example problems, feel free to ask that. And some people did that in this tweetback already. It would be great if you collect that maybe somewhere in the Moodle forum. Just open a thread for that. Ask for every questions that you want to discuss and want me to discuss in more details somewhere here in the course. And I'll be happy to at least pick a few of those, depending on the number of questions I get. I might not be able to do everything. But it would be nice if we could just collect that all in one place. And I'll take some of those when I have the time for that. I am planning to have 1 week at the end of the semester where we don't discuss any new topics. So similar to what we did before Christmas, there'll be 1 week dedicated to examples and questions, and we should have ample time to discuss hopefully most of your desired exam problems during that week at least. All right, so it would be great if those who asked on the tweetback already just open a thread on the Moodle forums and collected everything there so that I don't have to wade through multiple tweetbacks to get that all together. All right, so a couple of minutes left. That should be enough time to quickly discuss, 11.2. And basically that already states what you have to do. Compute the left and right limit of that function at 1. Of course, I could also have left out that first sentence and expected you to know what to do. So if I only ask, is the function continuous at 1, you still do the same thing. You compute the left and right limits, you conclude whether there is a limit, and then you check whether it has the same value as the function limit. Right? And in that case, well, what we have to do is, let's first compute the limit as x approaches 1, let's say from below. Maybe we write that in a more legible way. Right, so this here means x is strictly less than 1. And that means I can use this first expression for the function definition, where we have the expression between 1 and 0. So I can just substitute that for f. And I get x minus 1 over x squared plus 1. Well, then what happens if I just substitute the value 1 in here? Would be my first try, of course. Well, this here goes to 1. This here is obviously also 1. This here goes to 1, and this here goes to 1. So the numerator goes to 0, and the denominator goes to 2. So both limits exist and are finite. And that means I can just use them, because the denominator is not 0. Right? So no problems here. So I get the limit is 0. Okay, so that's the simple start. That's the limit from below. Now let's try for the limit from above. In this case, I use the expression for x equals greater than 0, right? Because it's coming from above. That implies x equals greater than 1. Sorry, not 0, 1. X equals greater than 1. So I can use this x to the third minus 1 over 6 minus 6x. Well, and of course, you'll see that if I just substitute 1, I get a 1 here, I get a 1 here, I get a 6 here and a 6 here. So the numerator again tends to 0. But now the denominator also tends to 0. That's unfortunate. So we can't just substitute. We'll have to try and simplify that first. And of course, we can immediately write the denominator as well. That is minus 6 x minus 1. Let's write it like this, just to have the x with a plus sign in this linear factor. I factor out a minus 6 instead of just a 6. And of course, I'd like to have something like that in the numerator as well. See if that's possible. So I'm going to try and divide x to the third minus 1 by this factor x minus 1. So let's see, first I need an x squared. X squared times x is x to the third. And if I multiply x squared with x minus 1, I get x to the third minus x squared. I subtract that. And that means the x to the third cancels out, of course. And then I get, x squared minus 1. Right, so I'll continue. Now I need to produce this x squared. So I need to multiply x by x, obviously. X times x is x squared. And now multiplying x by this factor, x minus 1, that will yield x squared minus x. So that's what I subtract. So I get x minus 1. And now I need to produce this x here. So obviously I need to add plus 1. 1 times x is x, and 1 times x minus 1 is x minus 1, and I subtract that, and I get 0. Right? So that means that polynomial division actually works out. And what I get here is, well, this is the same thing as the limit to 1, x minus 1 times, and now I'll take this expression here, x squared plus x plus 1 over minus 6 x minus 1. And now I can reduce this expression by x minus 1. Right, so that means this is the same thing as the limit of x squared plus x plus 1 over minus 6. So now this complication in the denominator just went away nicely. Obviously the new denominator tends to minus 6. For the new numerator we get 1 here, this tends to 1, this tends to 1, so the whole thing tends to 3. And that means our limit is 3 over minus 6, or minus 1 over 2. And now let's see. This limit from the left was 0. The limit from the right is minus 1 over 2. Maybe let's summarize that. So the limit coming from below, that was 0. The limit coming from above, that was minus 1 over 2. And obviously those two don't agree. And that means the limit at 1 doesn't even exist. Right? So the limit x tends to 1 of f of x does not exist. So if the limit doesn't even exist, the function can't be continuous. And if you look at the definition, the function value here is 2. 2 is neither of those, so neither 0 nor minus 1 over 2, so it's not even left or right continuous. Let me just add that. Not even left or right continuous. And there is no way to make this function continuous at that point. Right? If the limit had existed, we would have compared that to the function value 2. And well, two possibilities. Either the limit was 2, then the function is continuous, or the limit was not 2, then there is a continuous extension, but this function is not continuous because the function value is different from what it should be, basically. Yeah, but in this case, the question is moot because the limit doesn't even exist. All right, so this completes 11.2. Any questions about that? Yes. Yes, you can solve the problem with L'Hopital's rule as well. We'll talk about that next week when we introduce differentiation, because I need differentiation to talk about L'Hopital's rule, yeah. But of course, that would also be okay, unless I explicitly exclude it. I think I did that on some questions on that sheet, right? Didn't I? Yeah. The spelling is different. Yeah. I'm not quite sure what the correct spelling is. Probably there is no correct answer for that. It's all the same thing. Yeah. So unless I exclude it like I did here in 11.3, of course, in the exam, you're free to use L'Hopital's rule if you want that. Use whatever is easier. All right. Any other questions? Then I'd say that's it for today. I'll see you tomorrow for more continuity and bisection.